dear students. So I am Dr. Surya Sharma, Faculty of Physics at Institute of Aeronautical Engineering, Hyderabad. Today I am going to talk on the topic called Nanoscience and Nanotechnology. So let us see the introductory part. What is nanotechnology? So nanotechnology is the control of matter on the atomic level. So it is the ability to build using atoms as building blocks. So nanotechnology is used to manufacture the novel materials with different innovative novel properties. So in the day-to-day developing subject with large number of applications. So there has been much debate on the future on applications of nanotechnology. So nanotechnology has the potential to create many new materials and devices with wide-ranging applications such as in medicine, electronics, and energy production. So what is a nanometer? So 1 nanometer is equals to 10 power minus 9 meters, which is equals to 0.000000001 meter, which is equals to 1 billionth of meter. So what is a nanostructure? So structure with at least one dimension less than 100 nanometers is what we call it as a nanostructure. So people mostly used definition in nanoscience and nanotechnology is concerned with nanoscience is the study of the phenomena and manipulation of materials at atomic, molecular and macromolecular scales, where properties differ significantly from those at larger scales. Whereas the nanotechnology is the design, characterization, production and application of structures, devices and systems by controlling the shapes and size at nanometer scale. So if you come to the origin of nanotechnology, so there has been much debate on the future on the implications of nanotechnology, and nanotechnology has the potential to create many new materials and devices with wide-ranging applications such as in medicine, electronics and energy production. So why we study nanoscience and nanotechnology? So nanoscience, so as we told, the study of fundamental principles of nanostructures between bulk and the atomic properties. And nanotechnology, the application of nanostructures into useful devices. Now, if you come to the origin of nanotechnology, so the word nanotechnology is relatively new. So the existence of nanostructures is not new, but so in 4th century AD, Roman glass makers fabricated glasses containing nano-sized materials. Similarly, gold nanoparticles are made long ago. The concept of nanotechnology was first given by a famous scientist in the year 1959 by Richard Feynman, by giving a principle. There is a plenty of room at the bottom. So the principles of physics, as far as I can see, do not speak against the possibility of maneuvering things atom by atom. So the concept of nanotechnology was given by Richard Feynman in 1915, right? So in the 18th century, British scientists Thomas Wedgwood and Sir Humphrey Davy were able to produce images using nitrate and chloride, but their images were not permanent. So in 1960, Richard Feynman presented a visionary and prophetic lecture at a meeting of American Physical Society entitled "There is a Plenty of Room at the Bottom," where he speculated the possibility and portent of nano-sized materials. So the term nanotechnology was defined by Tokyo University professor Norio Taniguchi in the year 1974 as in his paper as follows, that is, nanotechnology mainly consists of the processing of separation, consolidation and deformation of materials by one or by one atom or by other atom or by one molecule. So according to Richard Feynman, the principles of physics, as far as we can see, do not speak against the possibility of maneuvering, according to the possibility of maneuvering things atoms by atom. It is not an attempt to violate any laws. It is something in principle that can be done, but in practice it has been done because we are too big. So at nanoscale, nano means atoms are extremely small and the diameter of a single atom can vary from 0.1 to 0.5 nanometers. So the diameter ranges from 0.1 nanometer to 0.5 nanometer depending upon the type of the element. So the radius of atom can be considered as the half the distance between the radius of the atom can be considered as half the radius distance between neighboring atoms when they are present in the solid phase. So why nano is interesting? The nano is interesting because the particles are small and we have the property called high surface to volume ratio, which react differently to new properties, interact with the light differently, or on the scale of small biological structures, and meets the relations between the quantum physics and the classical physics. Interesting new structures, interesting materials with nanoparticles embedded. So why nano is interesting? So here the particles are small, they are high surface to volume ratio, and react differently and act differently to the new properties, interact with light differently, and are on the scale of small biological structures. And it brings the correlations between the quantum mechanics. So quantum mechanics meets the classical mechanics. And interesting new structures will be developed. So interesting materials with embedded nanoparticles can be obtained. Then 1970, so in the year 1970, so nanotechnology was coined, as I told you, by a Japanese scientist called Taniguchi. So in the 1891, the first atom seen, and in 1986, Engines of Creation, the comic age of nanotechnology by Richard Drexler. So that is why nanotechnology is the principle of atom manipulation, atom by atom, through control of the structure of matter at the molecular level. It entails the ability to build molecular system with atom by atom precision, yielding a variety of nanomissions. Now, this is the trend what we follow when the technology has been developed to very new extent by using sophisticated devices, coming to the nano devices. So if you come here, so why nano is interesting is what we have seen, the particles are small and the properties concerned with the particles are small are high surface to volume ratio, react differently, act differently, interact with light in a different manner, and brings quantum mechanics with meet classical mechanics. So interesting new features, and the new nanoparticles are embedded in the materials. So now, why the properties of nanoparticles are different? There are due to phenomena to which the properties of nanoparticles are different. So why the properties of nanoparticles are different in the sense, so these properties of nanoparticles are different because of two cases. One is the surface area to volume ratio and quantum confinement effect, right? So these are the two cases why we need to explain the phenomena where properties of nanoparticles are different. Why the properties of nanoparticles are different. So if you come to the first one, that is increase in surface area to volume ratio. So nanomaterials have larger surface area. Nanomaterials have larger surface when compared to the same volume or mass of the material produced in larger form. So if you consider a sphere of radius r, so its surface area is given by surface area of a sphere is 4 pi r square. Surface area of a sphere is 4 pi r square. So its volume, because increase in surface area to volume ratio, right? Its volume is 4 by 3 pi r cube. Surface area of a sphere is 4 pi r square and the volume of the sphere is 4/3 pi r cube. So surface to volume ratio. So surface to volume ratio can be given by surface to volume ratio is given by, so surface area of a sphere is 4 pi r square by 4/3 pi r cube. So surface to volume ratio can be given as S by V is equals to 3 by R. So as R decreases, surface to volume ratio increases. So as R decreases, surface to volume ratio increases. So the properties of materials will be, changing, because as the radius of the surface, as R decreases, right? So R decreases, so surface to volume ratio increases. So the properties of materials will be changing. If the material has high surface energy, if it is small in size, or vice versa. If R is more, then surface to volume ratio will be, if R is more, then surface to volume ratio will be less. If R is less, then surface to volume ratio will be more. So that is what the vice versa condition we explained. So if as the surface to volume ratio increases, the material possesses good catalytic process. As the surface to volume ratio increases, the material possesses good catalytic properties. Thus, nanoparticles show enhanced stability and broader for scope of different applications. In some cases, materials that are inert in their larger form are reactive when produced in their nanoscale form. This affects their strength or the electrical properties. So regarding the number of atoms with respect to size, we can give an example, that is, a particle of size 30 nanometer has 5% of its atoms on its surface. At 10 nanometer, 20% of atoms at 10 nanometer, 20% of its atoms, and at 3 nanometer, 50% of its atoms. So this is what we explain when we speak about the increase in surface area to volume ratio. So the other phenomena which explains why the properties of nanoparticles are different is the quantum confinement effect. So when atoms are isolated, the energy levels are discrete. As we see, when we speak about the quantum mechanics, the energies are quantized. The energies exist in terms of integral multiples of energies. In the same way, so when atoms are isolated, the energies levels are discrete. When very large number of atoms are closely packed, to form a solid, the energy levels split and it forms certain bands. So nanomaterials represent at intermediate stage. When the dimensions of a box or wells in which a particle is represented are of the order of de Broglie wavelength or mean free path of electrons, energy levels of the electrons change. This effect is what we call it as the quantum confinement effect. When the material is insufficiently small in size, around typically 10 nanometers or less, organization of energy levels splits into the organization of energy levels into which electrons can climb or fall or can fall a change. That means there will be a change. So specifically, the phenomena results from electrons and holes. The phenomena results from the electrons and holes being squeezed into dimension that approaches a critical quantum measurement called the excited Bohr radius. That means the existence of holes and electrons, right? The existence of holes and electrons. So this can affect the excited Bohr radius. So this can affect the optical, electrical, and magnetic behavior of materials, particularly as the structure or particle size approaches the smaller end of the nanoscale. In small nanocrystals or clusters or grains, right? So the electronic energy levels are not continuous, right? So the nanocrystals or clusters or grains. So the energy levels, the electronic energy levels are not continuous as in the bulk, but are in discrete because of the confinement of the electronic wave function to the physical dimensions of the particles. That is why the properties of nanoparticles will be differing. So that is why the properties of nanoparticles are different because of this point called quantum confinement. So the quantum confinement will be eligible. The quantum confinement will be eligible for the particles having the discrete energy levels or discrete energy packets instead of having in a bulk form. So that is the reason why the properties of nanoparticles are different. So one is a surface to surface area to volume ratio, and other is the quantum confinement effect, right? So these two are the two important cases which can be explained why the behavior of the particles will be differed at the nano range. So if we come to the fabrication of nanomaterials, so two basic approaches to make nanostructures involve either top-down approach or top-up approach. That means fabrication of nanomaterials can be done in two processes. One is top-down and other is bottom-up. So these are the two processes. These are the two important processes in which the nanomaterials can be fabricated. One is top-down and other is bottom-up. So in the bottom-up approach, let us see what is the bottom-up approach. In the bottom-up approach, the atoms or molecules and even nanoparticles themselves are used as building blocks for the creation of the complex nanostructures. So these processes are essentially highly controlled and complex synthesis techniques are required to fabricate this type of nanostructures, this type of nanoparticles. On the other hand, in the top-down approach, they rely on either adding a division or removal of a bulk material to produce the desired nanostructure with some desired properties. So they are inherently much simpler process when compared to bottom-up process. So out of these two processes, top-down and bottom-up process, top-down process is one of the easier method or one of the easier technique to fabricate a novel nanomaterials. So in top-down approach, nano objects are constructed from larger entities without atomic level control. So these seek to create smaller devices by using larger ones to direct their assembly. So the top-down process of preparing nanoparticles are effectively examples of solid-state processing of materials. Whereas in bottom-up approach, materials and devices are built from molecular components which assemble themselves chemically by principles of molecular recognition. So these seek to arrange smaller components into more complex assemblies. So nanoscale structures are normally achieved by chemical synthesis of materials in liquid state or gaseous state. So let us see what are some of the fabrication methods we can develop. Let us see what are the fabrication methods we can see for for fabrication of nanomaterials. So the materials which can be, so the methods to fabricate nanomaterials are, first one is sol gel method, right? So this sol gel method is also called bottom up method. So which is the second process, that is bottom up. And another method to fabricate is vapor deposition technique. Vapor deposition. Another method to fabricate a novel nanomaterial is vapor deposition technique, which we call, this technique is also called top-down process or top-down approach. So in vapor deposition techniques, we have two types of techniques, vapor deposition techniques. One is, in vapor deposition techniques, we have two types. One is the physical vapor deposition techniques, that is what we call it as PVD, and other is we call it as CVD. So that is chemical vapor deposition techniques. So physical vapor deposition techniques and chemical vapor deposition techniques have significant role for the fabrication of nanomaterials. So this physical vapor deposition technique includes first one is the DC magnetron sputtering. So sputtering is one of the mechanism. DC magnetron sputtering, RF sputtering, pulsed laser deposition, So these are the physical vapor deposition techniques. When come to chemical vapor deposition techniques, so they include E-beam technique, electron beam evaporation, right? E-beam evaporation techniques, that is electron beam evaporation, and synthesis, that is what we see, synthesis vapor, chemical reactions. So these are the different techniques in which we can fabricate the novel nanomaterials. So let us see one by one what are the different process, what are the different cases how the nanomaterials can be fabricated. So as we saw, the nanomaterials can be fabricated either by a bottom-up approach and top-down, either by using PVD or CVD, where PVD is the physical vapor deposition, CVD is the chemical vapor deposition, right? And we have seen some of the deposition techniques, right? Now, let us see what is a sol gel method. What is sol gel method? That is called a bottom-up. Let us see what is bottom-up or sol gel method. Right. Sol gel involves the formation of colloidal suspension of solution and gelation of the solution to form nanoparticles into a continuous liquid phase, that is in the form of gel. Right. Initially, a homogeneous solution of materials is prepared and used as precursor for nanofabrication. The solution is deposited on a suitable substrate by spraying, dipping, or by spinning. Okay, it is kept for a while for gelation. That means once it is spinned, that means if it is once spinned or sprayed on any substrate, if you take a glass substrate and if you deposit some material, right? If you deposit some solution on this substrate, so we have to keep that particular substrate until it gets dried. That means it should be getted in the form of gel process. Should be like gel, right? So it should be, that is what, if the sole is deposited on a suitable substrate by spraying, dipping or by spinning, it is kept for a while for gelation. So during this gelation time, the material gradually loses its fluidity, right? And undergoes a transition from viscous liquid from viscous liquid state to elastic state, elastic solid state. That means there is a phase transition from a liquid state to solid state. So this depends upon some certain parameters like viscosity, right? Temperature, viscosity, temperature, etc. of the solutions what we take. So in sol gel method, the nanoparticles formation involves certain steps, right? So the desired colloidal particles are dispersed in a liquid to form a gel. So the deposition of the solution on the substrate by either by spraying, dripping, or by spinning, right? The particles in the sol gel are polymerized through a removal of the stabilizing components and produce a gel. So the final treatments paralyze the remaining organic or inorganic components and forms either a crystalline form or a amorphous form of the nanoparticles coating on the substrate. So the main benefits of sol gel processing, the high purity and uniform nanostructure that can be achieved at very low temperature. So that is one of the main advantage of using sol gel method. Right? It is normally used to produce metal oxide nanomaterials. So the sol gel method has its own advantage, right? So advantage, that means it can be, we can obtain the purity, we can obtain the high purity and uniform nanostructure can be achieved at low temperatures. So it is normally used to produce metal oxide nanomaterials. So if you go to the other process, that is called vapor deposition process, that is called top-down approach. So vapor deposition refers to any process in which materials in a vapor state are condensed through condensation. That's why we call it as, it's one of the physical vapor deposition technique, right? So condensation, chemical reaction, or conversion of liquid into different form, the conversion of liquid into other phase like solid materials. So these processes are used to form coatings to alter right, to alter the mechanical, electrical, optical, and magnetic properties. Okay, optical properties to avoid corrosional resistance and wear properties of the substrates. So vapor deposition techniques can be classified, as I've told you, can be classified as physical vapor deposition techniques and other is chemical vapor deposition techniques. So this physical vapor deposition techniques involves the conversion of solid material into gaseous material, right? It's PVD, that is what we call it as PVD, is a physical vapor deposition process which is used to convert a solid material into gaseous material by some physical process, which is then cooled and is again redeposited on the substrate as per the requirement, whatever the phases, whatever the pressure, whatever the temperature, what is the pressure, right, and what is the gas, how much SCM and all. You should consider while depositing a solid material, right, onto a substrate. So one of the best method which we can use for physical vapor deposition is the sputtering. So sputtering, as we know, that is the sputtering. The word sputtering has been existed from the word called sput. That means throwing something on the substrate. Right. So that is what we call it as sputtering. That means the atoms or molecules can be sputtered. Right, this gets sputtered from solid phase to from solid material onto the substrate in the form of gaseous form. Right, so all the reactive physical vapor deposition techniques, hard process combine have following steps. can be have some following can be having certain steps, right? So a method of depositing material, right? Combination with active gas such as nitrogen, oxygen, or methane. So there is a bombardment of plasma. There is a bombardment of plasma of the substrate to ensure a dense hard coating, right? So these PVD methods differ in the means for producing the metal vapor and the details of plasma creation. So the primary physical vapor deposition methods are iron plating, ion implantation, sputtering, and laser surface alloying. And thermal evaporation is one of the simplest and most popular synthesis technique, and it has been very successful. Thermal evaporation technique has been very successful and versatile in fabricating a nanomaterial. And nanomaterial in the form of wires or belts or some other nanowires or nanobelts with different types of characteristics. Okay. So we can have multi-wall and single-walled carbon nanotubes also have been successfully fabricated in the system using hydrogen and methane and different reactants. So metal catalysts such as gold, tin, copper, etc. have also been used to achieve size control alignment. So these are the certain properties. So these are the certain properties which we can explain in case of physical vapor deposition techniques. So in chemical vapor deposition techniques, so this CVD is widely used for depositing thin films for a large variety of materials. So these applications of CVD, chemical vapor deposition techniques, range for fabrication of microelectronic devices to the deposition of protective coatings. So in typical CVD process, reactant gases at room temperature enter the reaction chamber. Okay, so these are the certain factors, some of the certain fundamentals how we can go ahead with the fabrication of nanomaterials. Right? So that is what. So why nano is interesting? Okay, so why we should see what is a nanotechnology, why nano is interesting, and what are the properties that change from nanoparticles, how the properties are different, right? So these properties are different. This is all we can explain.
Like, share and subscribe. Hit the bell icon for more updates.